Today in AP Chemistry, we will be building a more sophisticated understanding of atomic structure and learn how to represent the distribution of an atom's electrons in a couple of different ways. Let's dive in with atomic structure. Now, this is the part of the class where I tell you that we've been lying to you for literally years about how the atom is structured. If you look on the bottom right, you'll see a diagram that probably looks very familiar because this is how we teach you the atom is built. And it's not all wrong, right? You see the protons and the neutrons together in the nucleus. That's true. You see the electrons outside of that area, and I've told you it's in a diffuse cloud, but you see that they are not together in the nucleus. That part's also true. What isn't really true is where exactly they are and how they're moving. So the Bohr model describes the electrons moving in fixed spherical orbits and staying in those same stable positions according to their energy level. So we learn the energy shells, right? The inner shell, the next shell, and we assume that that's where those electrons are just hanging out in those fixed orbits. And that part isn't true. So let's get beyond that model and learn what's actually happening. The problem is that it turns out this model only accurately describes a hydrogen atom. It is not accurate for any of the others, and looking at the table, there are a lot of others. So if we really want to understand what's going on, we have to have a more accurate model. The challenge is that you cannot actually observe exactly where an electron is and where it's moving. So if we're trying to build an understanding of where it is, where these electrons might be found, we can't just look, And the reason why, if you look at the diagram, remember, electrons are super duper, super tiny particles. And how do we look at something? How do we observe it? We bounce something off of it. We don't think of it like that. But if something is going to be observed, for example, by your eyes, light particles, photons, need to bounce off that thing into your eyeball and then interact with your retina, etc., right? Well, when we try to do that with the electron, because it is so tiny, bouncing a photon off of it actually knocks it out of the way. So wherever it was going to be going, after you, quote, looked at it, it is no longer going there. It's no longer where it was, and it is now on a different path. So the challenge of figuring out exactly where the electrons are is more complex than it might originally appear. So we can't figure out where the electrons are just by observing them. So what are we going to do? Enter Erwin Schrödinger and a bunch of complicated math. He created a probability model to determine not exactly where they are, because again, we can't do that, but where they are most likely to be located. This model is called the quantum mechanical model or quantum mechanics, and it will predict where the electron is going to be about 90% of the time. All right, this next bit is describing sort of the next whole topic we're going to get into. So I just want you to get this little preview and listen to these levels of organization. The quantum mechanical model describes multi-layered organization for where the electron would be, starting with an energy level. This is the most broad layer, is most similar to what you have learned. You can kind of think of it, they even call them shells. You can think of it as similar to the spheres that you're used to in the Bohr model. But within each of those energy levels are sublevels. And within each sublevel, the probability model that he created predicts this path of likely location for the electron that's called an orbital. So lots to know about these. We're going to get into that next. The different orbitals have characteristic shapes. We will get into those one by one, but this is a little bit of a preview of where we're going. I've organized this next section as like a tour of the energy level, starting with the lowest energy level, the one closest to the nucleus, the first one. This n equals 1 refers to that first energy level. So each of the layers of organization in this quantum mechanical model gets what's called a quantum number. The great news is that that's no longer part of the AP curriculum, and I feel like putting that on while you're learning the other stuff actually makes it more confusing, with the exception of this N, because you see it all the time, and I do think it's good to know that the N refers to the energy level, so N equals 1, the first one. All right, the first energy level has only one sub-level. Remember, that's an area where the electron can be, and that's called the S sublevel. You can see we would abbreviate that as 1S, 1 for the first energy level, S for the S sublevel. S sublevels only contain one orbital, and that orbital is shaped like a sphere. So if you look on the picture on the right, you can see the 1S, 2S, 3S, they just get bigger. Each orbital can hold 2 electrons. So putting together everything we've just learned, that means that that orbital in the S orbital can hold 2. That's the only sublevel in the first energy level. And that means that the first energy level can only hold 2 electrons maximum. Now, every energy level has an S sublevel. Okay? It's not unique to the first one. It's just first seen in the first one. The other energy levels have S plus other stuff. So let's get into that. The second energy level, we see N equals 2. It does have its S sublevel. We call that 2S. Like I said, they all have the S. That one can hold 2 electrons, but it also has a P sublevel. We would call that 2P. 2 for the second energy level, P to describe the sublevel. So let's learn about those. P sublevels contain 3 orbitals, and they have a different shape. You can see down below, they are shaped like dumbbells. Each of those orbitals can hold 2 electrons. So when you put that all together for the P sublevel, that means the P sublevel can hold 6. So putting everything we've just learned together, if the S sublevel can hold 2 and the P sublevel can hold 6, what's the maximum number of electrons that can inhabit the second energy level? That would be 8, yes. The third energy level, or N equals 3, remember we said they all have an S sublevel, so we would call its S sublevel 3S, and that one can hold 2. It also has a P sublevel, we would call that one 3P, and we know the P sublevels can hold 6 electrons, but in addition to those, it has a D sublevel, which we would call 3D. So let's learn about those. The D sublevels contain 5 orbitals, most of which are shaped like a double dumbbell. You could look on the side. There's that weird one in the middle. You're not going to be asked to draw this or anything. Not harmful to be able to recognize them, but it's more what you're going to really be asked to do is sort of use this in terms of figuring out where the electrons are. I wouldn't get too caught up in the shapes, really. You do need to know that, as always, each orbital can hold 2 electrons. So if there are 5 orbitals in a D sublevel, that means that this D sublevel can hold a total of 10. So let's work backwards and figure out the total number of electrons that can be held in the third energy level. We got the 2 from the S, the 6 from the P, and the 10 from the D sublevels, and that adds up to 18. And finally, the fourth energy level, N equals 4. Again, it has its S. We call that 4S. That can hold 2. It has its P. 4P can hold 6. It has its D. That's going to hold, we call that 4D. That's going to hold 10, but it also has an F sublevel. You can see in the picture of the right, for whatever reason, the gold and red, it looks like pigs in a blanket gone totally wrong, fourth dimension style or something. The shapes are totally wacky. And again, you don't need to get too caught up on this. You need to kind of understand how many electrons it can hold and the ramifications of that more than this. But you should know that it has 7 orbitals with complex shapes. So that's all you need to know, complex shapes. And as always, each orbital can hold 2, and that means that the F sublevel can hold a total of 14. So if you add all of those up, going from its S all the way to its F, what's the total number of electrons that can be held in the fourth energy level? That would be 32. I know that is a ton of information, And it's going to take a little bit of like thinking it through and practicing to kind of keep it all straight in your head. So I put this little table in your notes just to help you organize it. So left here we have the energy levels, the sublevels found within, the number of orbitals for each of those, and then the maximum number of electrons, which is of course just 2 times the number of orbitals. You might want to annotate to just add up the maximum number of electrons, the 8, 18, and 32, because you should know that. And then just notice that each energy level, N, has exactly N sublevels in it, meaning energy level 1 just has the S, that's just 1 sublevel. Energy level 2 has S and P, and that's 2, etc. That can help you predict distribution, which could be useful later. So how can we put together what we just learned with what we know about the periodic table? To be honest, we've barely touched the periodic table, and we've only begun starting to learn about all the information that's held here. But even now, you know how many electrons each element has by looking at its atomic number, right? A neutral atom will have the same number of positively charged protons as it does negatively charged electrons, and that number is right above the chemical symbol. So for example, we can just look and see that beryllium has 4. So if we have an idea of where electrons would live and we know how many electrons each element has, we could communicate about that by drawing a picture of, the different orbitals that it has. But you can see, even with this like overly simplified version of what that might look like, yes, you can see some patterns emerging, but it's really impossible to glean any information. So we need a better way of communicating about where an atom's electrons live, and that is our next topic. One of those ways is electron configuration. Electron configurations use symbols, letters, and numbers to describe where an atom's electrons live. So some of these are familiar. The energy level gets its number, 1, 2, 3, 4. This sublevel gets its letter, S, P, D, and F, and we represent the actual electrons that are inhabiting that orbital with a superscript. So that number, looking down here at lithium, that little number that's like where the exponent would be in the superscript, those describe the actual electrons. So how many electrons does lithium have? You just have to add up all the superscripts, and it has 3, which if you look in your periodic table, you'll see that's correct. It has 3. So these other ones are just describing where they are. So the 1 and the 2, the big 1 and 2, those are describing the first energy level and the second energy level. And the S is describing that sub-level. Make sure that you have written in this electron configuration and annotated so you can read the code. Okay, but to be able to write one of those out, you need to know the order in which the orbitals will get filled. And this is all based on energy. Remember, there is an attraction between the electron and the protons in the nucleus. Much more on this later. This is a huge deal. So they, quote, want to get as close to the nucleus as possible. That's just another way of saying there is an electrostatic attraction between the electrons and the protons in the nucleus, right? So the lowest energy, in other words, the most stable place for those electrons to be, is as close as they can possibly get to the nucleus. So they're going to fill in the lower levels, the first energy level that's closest to the nucleus first, and then move out. That also means they're going to fill orbitals that are closest to the nucleus before orbitals that are farther away. This principle of electrons filling lower energy orbitals first is called the off-ball principle, and we can use this to predict the configuration for an atom. So the order of filling that's listed is really listing those orbitals from the lowest to the highest energy. You don't need to memorize that, so don't freak out. You do need to be able to produce it, but it's very easy to use some little tricks to figure it out without having it memorized. And one of those is shown on the left. So if you list 1s, 2s, 3s like we do in blue, top to bottom, and then go to the 2s, hop over and start listing the p's, 2p, 3p, 4p, because remember 1 doesn't have a p. On and on and on, and then go down to 3 and start listing out the first place where there's a D at the 3, 3D, 4D, 5D, like we do in purple, etc. then you can predict the order of filling by doing this little diagonal arrow situation. So if you see the purple diagonal arrows, we're obviously starting at 1s, go arrow down, that's the first one. And you do the little scooch around with this lime green curve, and then you're doing 2s, scooch around again, and then you're going through the 2p and the 3s. That's going to put you in the order of filling. One thing that you may notice is that the 4s is going to be filled before the 3d, which feels like that's not matching what we were just talking about. We are going in levels of energy. And that is because the 4s orbital is actually lower in energy than the 3d. So it's not violating the Aufbau principle. Aufbau principle is sometimes violated, but this is not it. And if you're like, what, why? It's really complex because what's going on is due to their respective shapes as a sphere and then that like wacky shape that the 3D orbital would be, the 3s at first, when it's taking on an electron, can be closer, at least experience a stronger effective charge from the nucleus. But then these things are dynamic, so once they start filling in, the 4s will be higher. It's like complicated, and we don't need to know it. But I just thought if you're like curious, like what is going on, that's it essentially. So anyway, the bottom line is that the 4s is a lower energy than the 3d. So the Aufbau principle states that the lower energy will be filled first, and it is filled first. That's why you can't just list them in order that we learned them. You have to actually list them in their correct order of filling, and you have to have a little scheme for remembering that. A perhaps even easier way is using the periodic table. I printed a periodic table in your notes. It just didn't fit right in this spot. I think it's on the next page. So what I want you to do is color in and annotate your periodic table so that it looks similar to this. And let's look at it together before we use it to solve these configurations. Notice that if you start at the top left, we are describing where each of these is going to fill. And if you follow these patterns, it will tell you exactly the order. So we know that hydrogen only has one electron. So that one electron, of course, is going to inhabit its 1s orbital. But our 1s orbital can hold up to 2. So if you hop over to helium on the other side, it also is showing 1s because, of course, it only has 2, and that means that both of its electrons can inhabit that 1s orbital. With helium is a little bit of an exception because it's hanging out on its own because it just has the 2, right? But if you notice over here, all these light blue, these are all the first 2 in their respective shells. So the rows, or we call them periods, 1, 2, 3, 4, 5, 6, 7 from top to bottom, from helium down to francium. These are the next energy levels. And so when we're starting a new energy level, of course, we're starting at S. So we have our 1s, our 2s, etc. That makes these whole first 2 groups, which we will be learning all about this later. These are all part of what we call the S block. So we know that if we're counting and we land on lithium or whatever, its last electron is going to be in the 2s, right? 2 for the second energy level and S because it's part of the S block. Hop over to the green, and these are the P block. So if you are figuring out the electron configuration for boron, for example, you know it has 5 electrons. And if you just start at hydrogen, 1s, we have 2 filled there. We would call that 1s2. And then we have 2 for the third and fourth electrons, 2s2. And then we have 1 electron in its 2p orbital. And so we call that 2p1. We're going to build some of these so that you get practice in doing it, because I know just someone reading it aloud doesn't fully make it land. You're going to practice, but this is the key to understanding how to use the table for this. Notice we have down here the D block. Please note that the energy level on the D block is 1 less than that of the S and P that's on the same row in the same period. And that's for those reasons we said. The S and the P are, the S is is lower in energy level, right? So you just have to remember that. And then also remember that these F block elements, this section of the periodic table actually goes where this little red line is, right? The lanthanide and actinide series, that's what the LA and the AC here. These fit in there. We just don't normally put it there because that would make the periodic table too wide and like impossible to print and stuff, but that's where those go. So you have to fill those before you move on to the 5D, for example. You have to finish your 4F block before you move on to 5D. Okay, let's just do some of these, and then that's going to, I think, help you get an idea of how you can use this. All right, so let's use the periodic table to predict the electron configurations for neon, magnesium, and manganese. All right, let's just look at the answers and compare them to the periodic table, starting with neon. So first of all, find neon. It is a noble gas on the right, has 10 electrons. Notice that if you add up the superscripts that are shown in the electron configuration, it does add up to 10. 2 plus 2 plus 6, right? And we're just showing where those are. Here's how you do it. You're going to start up here at the top left. We know that both of these first two orbitals are filled, right? We're going to go all the way to 10. So we know we at least got 2. So we have filled that first energy level and its S sublevel. So we're going to go 1s2. Done. Going down to the next period, we know that we still have way more than just 2, right? So we're going to easily fill the 2s sublevel, and we're going to write 2s2. So that would be its third and fourth. Now we're over in the P block, right? And we're going to count 1, 2, 3, 4, 5, 6. That is just the exact right amount to fill that 2p orbital. So we're going to put a 6, and there are no more, so we are done. That's how we do neon. Next up is magnesium, and I want you to look through and compare its electron configuration to its location on the periodic table and how many electrons it has. Notice that, I mean, of course, on the day of the exam, you are not going to have a colored annotated periodic table, but if you do this, I'm sure you can kind of already see, if you do this quite a bit, you will just kind of internalize where those blocks are, and you can also use the little diagram scheme that I had just already showed you before. So we have our 1s2 filled, 2s2, 2p6, but if you look, magnesium here with 12 has 2 extra electrons compared to neon. So we need to use another sublevel, and we're going to fill the 3s2 there. And finally, here's just a long one. I'm not going to read this one all the way through for you, but you can just pause and compare its electron configuration to its location on the periodic table. So you can see this is a really powerful way of figuring out an electron configuration. So I'm sure you can already see how some of these electron configurations become really complicated and kind of unwieldy. So we have a shorthand for making it a little bit easier to write out. Compare neon and magnesium that we just did. Obviously, on the pathway to neon and the pathway to magnesium's full electron configuration, the first part of it is all the same because we have the same number of electrons, in the beginning. The only difference is that magnesium has 2 additional electrons that we had to distribute. So one way of showing this is just what we call noble gas configuration, or like shorthand notation. You can just do the chemical symbol for the previous noble gas. Remember, those are the ones on the far right, in brackets, not parentheses, in brackets. And then you just write out the configuration for the quote extra electrons that make it different from neon. So you can just compare those two. I put in blue and the core electrons, and then in purple, the outer shell electrons, or the valence shell electrons. Now listen, there is a ton that we're going to be learning about that. So don't worry about that if you don't understand. But we're going to right now just focus on how we would represent this in a configuration. So you compare those two, the blue and the purple, and you can compare also for sulfur. Here we have the core electrons written out, and then I put them in the noble gas configuration. All right, now I want you to try one, and I want you to try it with this little chart thing. I've printed it here. I would like you to learn how to write it out yourself. I'm sure you can see, like, it's not that hard to learn how to do, and it's kind of a nice thing to have in your pocket. You'll figure out which method, the periodic table or this, you like the best, but I want you to learn both. And we're going to write out the ground state electron configuration of platinum and barium. And you should know what ground state means. This just means the electrons in their lowest energy states. We'll contrast that with other states later, but that's what that means. It just means like the regular one. All right, so pause here and try it using the little chart, or maybe you could do one with the chart and one with the periodic table. You do you. Pause. All right, did you get it? If you did, great. If you're feeling super confused, we can talk about that in class. If you almost got it, but you're like, oh, I get it in general, but I just made a mistake. Oh, that's great too. Good job. All right, for this one, I want you to, using whatever method you are preferring right now, to write both the longhand and the shorthand or noble gas electron configuration for titanium and iodine. Pause here. Did you get it? Amazing. Great job. Our last topic and the other way to represent the distribution of electrons for an atom is something called an orbital diagram. So let's do that now. The purpose of these is to provide a little more detail about what's going on with the electrons. Because remember, if we, for example, are saying that an element has its 2p sublevel filled, that's just all 6 of those electrons kind of in the same pot, right? We don't know that much detail about exactly where they are. An orbital diagram will give that extra level of detail. This is a symbol system that uses boxes to represent the orbitals and arrows to represent the electrons. We'll get into, so you can see it on the right, we'll get into like how to make this, but I just want to give you like a preview. Visually just compare the number of electrons total to its electron configuration and then the orbital diagram. And I know it says electrodes, just, I liked this, so I just kept it anyway. All right, good job. Let's move on. To properly fill out our orbitals, we have to consider 2 rules, Pauli exclusion principle and Hund's rule. You don't need to know what these are called, but you are expected to apply them, so we're going to talk about it. All right, so the first one, Pauli exclusion principle, says that each particle needs its own unique address, place. So for electrons, that means if 2 electrons are sharing the same orbital, as we know that they do, the difference in their, quote, address is going to be what we call their spin. There's a bunch of physics there. We're not in physics, thank goodness. The chemistry is the best. And we're going to instead just say that one has an up spin and one has a down spin. And you can see the arrows. That's what the arrows are representing, is their spin, and they have to be opposite. So you can see on the left diagram that the 2 with the X don't work because they have 2 electrons with the same spin and the same orbital, and that is not allowed. They have to have one arrow pointing up and one arrow pointing down. Hund's rule says that electrons will fill orbitals one at a time before pairing up, which makes sense when you think about it, because remember, these have a negative charge and 2 like charges are going to repel, right? So if they can spread out a little bit and not be right next to one with the same charge, then of course they will. And that's why you would represent that in the way that's shown in the Hund's rule diagram with the green check. And that would be if you have 3 electrons filling, for example, a 2p sublevel, you're going to have them filling each of those orbitals separately, and they would not immediately pair up like you have. And notice also in the ones that are not allowed, notice also they're going to have the same spin. So you're going to, when you're distributing, you're going to do like up, 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 and then you would go back and fill with the down and the down and the down if you were filling up all 6 spots. The good news is that if you can do an electron configuration, you've kind of already done the legwork for figuring out the orbitals. You would draw boxes for each of the orbitals that are needed for that particular element, and then you just start distributing electrons according to the rules that we just described into the orbitals that you have just drawn. So you can see hydrogen, helium, lithium. We have 1, 2, and 3 electrons. And I just want you to kind of analyze the orbitals and notice how they match the rules that we just said and how they also correspond to the electron configuration that we learned before. Let's dive in and try one. So we're going to draw the orbital diagram for boron. So first we need to figure out how many electrons it has. So look on the periodic table, pause for a sec, look on the periodic table, how many electrons? Correct, there are 5. So which orbitals are needed? You can get this directly from the periodic table of which you've had a little practice, or use the periodic table to write, or the little diagram thing, to write out the electron configuration if that helps you. Like ultimately, if they're not asking for the configuration, they just want the orbitals and you feel comfortable, you can skip that step, but let's do it. Here's the electron configuration. We have those 5 electrons. The first 2 are in the 1s, the second 2 are in the 2s, and the last one is in the 2p. So now we're going to draw squares for our orbitals and fill them according to our rules. So pause here and see if you can do that. All right, and here we go. So we had 1 up for the 1s, and then we're going to go 1 down to fill that. Moving on to the 2s, 1 up, and then 1 down to fill that one. And then that additional 1, we are just going to put an up in the first orbital for the 2p. And there's something special about the electrons that are not sharing an orbital. We call those unpaired, and they will make an atom more reactive. Again, more on this later. Notice also here that we have electrons that are in the core here, in an inner shell or an inner energy level, and then these last 3 are in the 2 energy level, the second energy level. These are the outside electrons or the valence electrons. All right, last one. We're going to draw the orbital diagram for aluminum. So what's the question you need to ask yourself first? Yep, you got to figure out how many electrons. So look on the periodic table, pause. There are 13. Now I recommend you write out the electron configuration. 1, that's just good practice. And 2, that will help you figure out the orbitals that you need. So pause here and do that. And there it is. Now you're going to turn these sub-levels in the configuration into orbitals and fill them. So pause here and try it. All right, did you get this? This is one of those things where you will all get this if we do like a bit of practice. Like you can totally get the hang of it. Which are the valence electrons? And I know we barely talked about valence electrons. This is a challenge question at this point. So anybody? And those would be the 2, 3s and the 1, 3p because they are in the outer shell. All right, great job. I will see you tomorrow.